Okay, so this is a walkthrough of how to solve the second task of today. And what I will do is just walk you through my Python script. And okay, so here we go. Well, first I of course read in the text. I read in the compact file, the one that doesn't have spaces and like different size letters and so on. And then I just check if I read in the file correctly. So let me try that. So here I read in the first part of the ciphertext, fine. Okay. I define myself a dictionary. I give each letter of the alphabet a number. I have the alphabet in capital and small letters here. I make myself a little function that can count the frequencies of each of the letters in a string. So say I'm given a list of characters, then this function returns a list where each index is the frequency of that letter. Then I guess the key length. So this is, I make this a variable so I can change it. So I try it with 3 first. I create some sublists. So these will contain the subsets of the ciphertext, which are encrypted using the same key. So the sublists, I do this little script in order to split my ciphertext into the sublists. So let's just test if this works. So here I make 3 sublists because I have guessed that my key length is 3. So the first sublist has every third letter starting with the P here, the first P, then the second P, and then the U, right? So P, P, U, this one starts with. The other one has I, and then E, and then C, I, C, and so on, right? So I take the encrypted text and I split it so that each sublist is now encrypted using the same key. Now the task is to figure out which key is each sublist encrypted with. So the way I do this, well, actually the task is first to guess the key length. So what I do is I take each of my sublists and I count the frequency of each of the letters in each of the sublists. And then I print out the maximum frequency. And here I print out not just how often it occurred, but like divided by how many letters there were in total in the sublist. So what I print is what I print is the frequency of the letter that occurs the most often divided by the number of letters in the sublist. So let's try that. So if I do this, oops. Okay. Then task 2. Come on. Solution. There we go. That. I. Okay. So here we see I get 3 prints, 1 for each sublist. And we can see here that the letter that occurs the most often occurs a little bit less than 8% of the times for each of the lists. And now we know from the slides that E should occur about 12%. 12% of the letters should be an encrypted E. So the most frequently occurring letter should occur about 12% of the time if I guess the key length correctly. In fact, 8% is about what you would expect for a random string. So 8% is 1 over 26. So that's the frequency if like every letter is equally likely. So therefore I know I haven't guessed the key length correctly because there should be a letter that stands out. So let's try to. I love Windows. So let's try to guess another key length. Okay. And here we get the same. Now we have 4 sublists because we have another key length, but still we get 7 to 8% for the maximum occurring letter. So I change this to 5. Let's see. And here, oops, like something specific happens, right? Here, all of a sudden, the most frequent letter jumps up to about 12%, which is what we were looking for. So now we know that we've guessed the key length correctly, or we expect that we've guessed the key length correctly. So now the task is to figure out, well, then how do we then decrypt now that we've guessed the key length? And actually, since this is just like, since each sublist is just encrypted with the CSAR cipher, all we need in order to decrypt each sublist is to know the shift that has been applied to that sublist. And actually, because we know the letter that's occurring the most frequently in each sublist, and we know that that was an E, or well, we expect that that's an E, that gives us actually the shift for each sublist. So, I mean, we can just calculate the shift as, you know, what's the letter that has the highest frequency, and then minus what's E, and then we know how much has the cipher shifted the text. So we can print these shifts, right? And it seems like the first one has been for the first sublist the shift is 3, and for the second one the shift is 0, and so on. Right. And then let's test if this was correct. So let's just test a little bit of the message that we get out if we try to decrypt with these shifts. And what we get out is midway upon the journey. So that looks good, right? So let's apply it to the original text. And here there's a little bit of bookkeeping because we like the spaces, we don't re-encrypt, and we need to keep track of big and small letters, and like punctuation is not encrypted either. So like there's a little bit of bookkeeping here. But then this should give us the correct text. And we see that this is indeed a meaningful text, right? Okay, so here, I mean, I've taught this a couple of times, and there seems to be always someone who asks like, so wait, how do you decrypt each of the sublists? How did you know how to, what shift to apply to them? And the answer is, I mean, I'll just repeat this, is that, so for each of the sublists, we found the letter that occurs the most frequently, and we expect that letter to be the encryption of E. So because we know we know what E is encrypted to, we can use that to find the shift. And then that gives us a shift for each of the sublists. And because each of the sublists is just encrypted with the CSAR cipher, that's all we need. The shift is all we need to decrypt the entire sublist. And then we just paste them all back together. Of course, this works because each of the sublists is just encrypted with the CSAR cipher. If it had been something, I mean, if it had been another monoalphabetic substitution cipher, we would have had to use frequency analysis and like smart guessing for each of the sublists individually. But that would also be possible.